Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Welcome to Simple Gyan. In this video, we will select a transformer for an industrial plant step by step, starting from the load list and ending with a practical transformer specification. The important idea is that transformer selection is not just a kW to kVA conversion. A transformer that looks adequate in a spreadsheet can still create unacceptable voltage dip when a large motor starts, overheat under harmonic current, or produce a fault level beyond the switchboard rating. We will use one complete worked example and test the result against demand, power factor, planned growth, motor starting, harmonics, cooling, short circuit duty, and reliability. Here is the opening question. If a factory has 2,000 kilowatts of connected equipment, must it buy a 2,500 kVA transformer? Most people add every nameplate, divide by an assumed power factor of 0.9, and round upward. The surprising answer is no, not automatically. Connected load tells us what is installed, not what will run at the same time and at the same loading during the plant's real peak. In our example, a proper demand study will lead to a 1,600 kVA candidate. The word candidate is important. It is accepted only after it passes starting, thermal, harmonic, fault current, and reliability checks. Why do manufacturers rate transformers in kVA instead of kW? Because the transformer must carry current whether that current produces useful work or supplies reactive magnetizing demand. Kilowatts represent real power that produces shaft work, heat, light, or process output. kVAR represents reactive power needed by magnetic fields in motors and other inductive loads. kVA is the combined apparent power seen by the transformer. Copper loss mainly follows current squared, while core loss is strongly related to applied voltage and frequency. The basic conversion is kVA equals kW divided by power factor. At a power factor of 0.92, 1,000 kilowatts requires about 1,087 kVA. The first engineering task is to build a load schedule. Group equipment by process function and record rated kilowatts, efficiency, power factor, duty cycle, starting method, operating mode, and whether each item is running, standby, or future. In this illustrative factory, the connected load is 2,000 kilowatts. Process sequencing and operating simultaneity reduce the expected maximum real demand to about 1,115 kilowatts. The demand factors shown here are not universal values. For an existing plant, the strongest evidence is interval meter data, operating history, and production schedules. For a new project, use process logic, equipment sequencing, and conservative scenarios agreed with operations. This chart shows why nameplate addition can oversize the transformer. The expected coincident demand is 885 kilowatts lower than the connected total, a 44% reduction in this example. But diversity is not permission to invent a smaller number. The reduction must be supported by real operating evidence. Examine representative interval data, seasonal peaks, shift patterns, shutdown startups, and unusual production campaigns. Also distinguish redundancy from demand. A standby pump may add little to normal coincident demand, but it can become part of a post-failure operating case. Now convert expected real demand to apparent power. 1,114.5 kilowatts divided by a power factor of 0.92 gives approximately 1,211 kVA. This example includes a documented 20% expansion plan, producing about 1,454 kVA. The next suitable standard candidate is 1,600 kVA. That transformer would operate at roughly 76% during the present peak and about 91% at the planned future peak. Growth allowance should represent known projects or reasonable uncertainty. Avoid stacking several unrelated safety margins on top of already conservative assumptions. A transformer can pass the steady load calculation and still fail the motor starting test. Consider a 250 kilowatt motor at 433 volts, 94% efficiency, and 0.88 power factor. Its full load current is about 403 amperes. A direct online start at 6 times full load current can demand roughly 2.42 kiloamps. The 1,600 kVA transformer is rated for about 2.13 kiloamps at 433 volts. That does not automatically mean the transformer is too small, because starting current is temporary. With 6% transformer impedance, The incremental drop across the transformer alone is roughly 6.8% in the simplified calculation. A proper study must include upstream impedance, running load, cables, motor torque speed data, and acceleration time. If the dip is excessive, consider a soft starter, VFD, suitable star-delta start, a different starting sequence, or a revised electrical architecture. Transformer percentage impedance is a design trade-off. Lower impedance improves voltage regulation and reduces motor start voltage dip, but permits more short-circuit current. Higher impedance limits fault current but causes more voltage drop. For a 1600 kVA transformer at 433 volts, rated current is about 2.13 kA. If impedance is 6%, the idealized short-circuit current at the low-voltage terminals is approximately rated current divided by 0.06, or 35.6 kA. The final study must include utility source strength, high-voltage network, and cable impedance. The result determines breaker interrupting rating and the short-circuit withstand of switchboards, busbars, and cables. Modern factories contain nonlinear loads such as variable frequency drives, UPS systems, rectifiers, switched-mode power supplies, and welding equipment. These loads distort current. High-frequency components and increased RMS current create extra copper and eddy current heating even when real kilowatts appear normal. List nonlinear load kVA, current total harmonic distortion, dominant harmonic orders, and neutral current where single-phase electronic loads are significant. A K-rated transformer is one possible solution, especially in low-voltage dry-type applications, but it does not remove harmonics. The vendor may recommend D-rating, a specially designed transformer, drive isolation transformers, multipulse arrangements, active filtering, or another mitigation method. The transformer type depends on location and risk strategy. Liquid-immersed transformers are common outdoors and in dedicated transformer bays. They offer robust thermal performance, but require fire separation, oil containment, and environmental controls. Dry-type transformers are often installed indoors or closer to the load because they avoid an insulating liquid spill. They still require adequate ventilation and protection from dust, moisture, corrosive atmospheres, and accidental contact. State maximum and average ambient temperature, altitude, enclosure, ventilation, fire requirements, and noise limits in the inquiry. Cooling assumptions that are valid in a laboratory can fail in a hot, poorly ventilated transformer room. Transformer price is paid once, but losses are paid throughout the asset's life. No load loss is present whenever the transformer is energized, even when production is stopped. Load loss is mainly related to current squared. At 80% load current, the variable load loss component is approximately 0.8 squared, or 64% of rated load loss. Ask bidders for guaranteed no load and load losses, then calculate annual energy using the plant's actual loading profile and electricity tariff. A cheaper transformer may cost more over its operating life, while an unnecessarily large transformer may carry higher no load loss for years. Compare total owning cost, not purchase price alone. The correct kVA is also a reliability decision. One 1600 kVA transformer is simple and economical, but creates a single point of failure. Two transformers allow sectionalized operation and maintenance flexibility. However, two half-sized units do not automatically provide full N-1 capability. After one unit is unavailable, the remaining transformer, cables, breakers, and bus section must carry the defined critical or full post-contingency load. Transformers intended for parallel operation must have compatible ratios, vector groups, tap positions, impedance, and phase sequence. Protection and circulating current risks also require engineering review. A good transformer inquiry removes ambiguity. Specify rated kVA, frequency, high and low voltage ratings, vector group, neutral arrangement, tap range and tap changing method. Specify percentage impedance, guaranteed losses, temperature rise, and sound limits. Describe motor start duty, harmonic spectrum, load cycle, overload scenarios, and future expansion. State ambient temperature, altitude, enclosure, fire strategy, protection, metering, and accessories. Finally, reference the applicable IEC or Indian standards, utility requirements, efficiency rules, and the routine, type, and special tests required. Vendor engineering is most effective when the application data is complete. Let us combine the result. The demand study gives 1,115 kilowatts. At 0.92 power factor, that is about 1,211 kVA. With 20% plan growth, design demand is approximately 1,454 kVA, so 1,600 kVA becomes the candidate standard rating. It is still not the final answer. Confirm motor starting and voltage dip, harmonic heating, ambient and cooling, short circuit duty, protection coordination and reliability architecture. Only after all 6 gates pass should the transformer be ordered. So the final rule is simple: select the smallest standard transformer rating that passes every engineering gate: demand, power factor, documented growth, motor starting, harmonics, thermal conditions, fault duty and reliability. This method avoids both dangerous undersizing and expensive oversizing. In our example, 2,000 kilowatts of connected equipment did not automatically require a 2,500 kVA transformer. A defensible study produced a 1,600 kVA candidate, followed by the checks that make the choice safe. If this explanation helped you, subscribe to SimpleGAN for more practical industrial engineering videos, and share in the comments the largest transformer used in your plant.